Good morning all watching this video. Today in this video we will discuss moment of inertia from the chapter Rigid Body Dynamics of class 11th physics book. In this rigid body dynamics chapter we have discussed previously the center of mass and definition and formula for moment of inertia, and we have derived the moment of inertia for ring. But today we will go through the quick revision and again derive the moment of inertia for the ring. And for the detailed discussion on moment of inertia, you can watch Rishi sir's video on the Pragya School channel that you got the link in the application. So please watch, check out your application of the school regularly to get the information about all the updates. So we start here moment of inertia from the definition. Moment of inertia is a property of body to resist or oppose the change in the rotational motion. It is like the inertia in the linear motion. Inertia also resists or oppose in the change in the linear motion, and here moment of inertia does that job. So we start moment of inertia. Before that we discuss the basic formulas of moment of inertia. First we discuss the moment of inertia for the system of particles. Here we take an axis. There are a system of particles m1, m2, mn, like m3 and like mn. There are n particles in these systems, and these all particles are revolving around this given axis. And assume that this first object is a distance small r1, and second object a distance small r2, and this object a distance r3, and this object a distance rn. Then the moment of inertia about this axis is given as I equals to m1 r1 square plus m2 r2 square plus mn Rn square. So the moment of inertia of a system of particles is given as sum of moment of inertia of all the individual particles about this given axis. We can write this formula in the short form like this: I equals to summation mi ri square I from 1 to n. So we can write it in this form, but for the derivation we use this formula. But this is the system of particles, but in daily life we need to find out the moment of inertia of the rigid bodies. Rigid body in which the mass is distributed continuously. In the mass is distributed randomly. Your mass 1 is here, second is here, third is here, not regularly. But in the rigid body mass is distributed regularly. So we need different formula for that. Assume that this is the rigid body, and this in this body mass is continuous, distributed continuously in the complete volume, and here the axis about which it is rotating, and we need to determine the moment of inertia about this axis. Then we need to take a small component of mass dm. Assume that the distance of this component from its axis is small r. Then the moment of inertia for this particle is given, for this body is given as integration dm r square. Dm r square. Here dm r square, this is the moment of inertia of this small component about this axis, and the I, or we can say the integration of dm r square, is the moment of inertia of this entire body about this axis. So here we will use this formula to derive the moment of inertia for the rigid body. But before going to derive the formula for rigid body, we will go through the two theorems of moment of inertia, which we need in the derivation. And the first theorem is theorem of perpendicular axis. Theorem of perpendicular axis. And second one is theorem of parallel axis. So, theorem of perpendicular axis says that if in a rigid body we have two perpendicular axes, and the moment of inertia of this axis, assume that Iy, and moment of inertia about this axis is Ix. Then the moment of inertia about third axis perpendicular to the both of the axes, assume that this axis and moment of inertia about this axis Iz, then these are two perpendicular axes and third axis is perpendicular to the both of the axes. Then the moment of inertia for the perpendicular this third axis Iz is given as sum of moment of inertia about two perpendicular axes. So moment of inertia of an axis perpendicular to the two perpendicular axes is given by the moment of inertia, sum of moment of inertia of them. That means this moment of inertia of Iz is equal to the sum of moment of inertia of Ix and Iy, and these all three axes are perpendicular to each other. And according to the theorem of parallel axis, assume that there is a rigid body and here is the axis of rotation, and we know the moment of inertia about this axis, but we need to find out moment of inertia about this axis which is perpendicular to this axis and a distance small d, and assume that mass of this body is capital M. Then the moment of inertia of the parallel axis to the initial axis is given as I equals to I naught plus md square. This is the formula we use to derive the moment of inertia about an axis which is parallel to the another axis, and we know the moment of inertia of that axis, and we can use that formula to derive this, that in which the moment of inertia of first axis n plus m and the square of the distance between two parallel axes. So these two theorems we will use in the derivation of moment of inertia for different bodies. So first we derive the moment of inertia, or in this video we will discuss the moment of inertia for a ring, but